continue with this ideal and non-ideal solutions. What is ideal solution? Ideal solution is the one which obeys Raoult's law. A solution which obeys Raoult's law is what we call ideal solution. What do you mean by obeying Raoult's law? Means in a solution, the vapor pressure of solution is equal to XA PA naught plus XB PB naught. Whichever solution follows this law is ideal solution. That means obviously you can understand that whichever do not follow this is non-ideal solution, right. Then which type of liquids will form this ideal solution? What are its characteristic properties and which kind of mixtures do not follow this and what are their characteristics is what we are going to discuss now. The solution in which, suppose two liquids A and B forming a ideal solution. If you consider the two liquids A and B in which AA molecular interaction and BB molecular interactions should be same as AB molecular interactions. Again I repeat, in liquid A there will be some intermolecular force between the two molecules of A. Similarly, in a liquid B there will be some intermolecular force between the two molecules of B. AA molecular interaction, that is the intermolecular force in AA, intermolecular force in BB should be similar to the kind of intermolecular force that likely to form between A and B in a solution. That means the net forces acting between two molecules of A, between two molecules of B should be same as the force acting between the two molecules of A and B. Basically the meaning is both liquids A and B should be of similar properties. What do you mean by similar properties? Then which kind of two liquids will form this type of solution? Example like both the liquids A and B should be of similar structure, size and other properties, should be having similar properties. For example like benzene and toluene. Benzene and toluene, this mixture will form an ideal solution. As you know very well that the benzene and toluene properties are almost identical. Size, structure, everything is almost identical. Then other examples, N-hexane and N-heptane. I can put it like, in the case of organic liquids especially, those liquids which are homologues and do not vary much in their molecular weight, just differ the consecutive molecules of a homologous series, benzene, toluene differ by CH2, hexane, heptane differ by CH2, and also similar molecules having similar functional groups like ethyl chloride, ethyl bromide, both are having similar functional group, that is halogen, and alkyl group is same, right. Ethyl chloride, ethyl bromide, these kind of mixtures will form what you call ideal solution, because the properties of both the liquids are almost same, and when you mix also the kind of interactions between these two will be same as the interactions between the two benzene molecules, two toluene molecules is same as the interactive force between the molecule of benzene and molecule of toluene. Similarly here, so the interactions will be same. These kind of mixtures will form ideal solution, and these, for these kind of solutions, if you draw a graph, you will get this kind of graph as previously what we have discussed. Here is equal to XA PA naught plus XB PB naught. This particular pattern, the graph, we get it when you draw for mole fraction of any one of these liquids. If you draw it against the pressures, the vapor pressure of these two, mixture of these two liquids at any composition will be in between the PA naught and PB naught. This is what we call ideal solution, and these are the few examples, and like this other examples also we can write. Then what are the other characteristics, properties differ for an ideal solution, when a solution can be an ideal solution? That is, delta V mixing should be equal to 0, delta H mixing is 0, delta S mixing is positive, delta G mixing is negative. Means formation of an ideal solution is a spontaneous process. Thermodynamically, if you speak, the formation of ideal solution, because both the liquids are having same tendencies, same properties, similar properties. So the mixing of two such solution, two such liquids to form a solution obviously will be spontaneous. Delta G mixing will be 0, delta S mixing will be positive. Delta H mixing, what does it mean? Enthalpy of mixing is 0. That means when you are mixing two liquids A and B, neither heat is evolved nor heat is absorbed. That means absolutely there won't be any change in the heat content even after formation of the mixture when you compare it with the two pure liquids. Delta V mixing is 0, meaning is there is no change in volume even after formation of solution. Means suppose if you have taken 10 ml of benzene, 10 ml of toluene, the total volume is 20 ml. When you mix both of them, the resultant volume again will be exactly 20 and there will be not be any difference. Then it is ideal solution. So non-ideal solution means the delta V mixing, two liquids A and B if you mix 10 ml each, the resultant volume will not be 20, either it will be greater than 20 or less than 20. Such solutions is what we call non-ideal solution. So again, in brief, for an ideal solution, thermodynamical properties are such that delta V mixing is 0, delta H mixing is 0, no change in volume, no change in enthalpy upon mixing, entropy increases and free energy change becomes negative and the process is spontaneous, right, and it follows this graph, and all this is about the characteristics of ideal solution. Now after this, next we go to non-ideal solution. Okay, non-ideal solutions. Now non-ideal solutions means which do not obey Raoult's law, which do not obey Raoult's law, means those solutions in which vapor pressure of a solution is not equal to sum of the partial pressures of the two liquids in the solution. A solution in which vapor pressure of the solution is not equal to sum of the partial vapor pressures of the two liquids in that solution. That solutions are what we call non-ideal, which do not obey Raoult's law. Now, again here as you can see, when we are saying that vapor pressure of a solution is not equal to sum of these two, obviously there will be two possible cases now. One is Ps greater than XA PA naught plus XB PB naught, and Ps less than XA PA naught and XB PB naught. You will get two cases. Obviously, both the cases are possible. Now, those solutions in which vapor pressure of a solution is greater than sum of the partial pressures of the two liquids, that is what we call solutions with positive deviation, and those solutions in which vapor pressure of a solution is less than the sum of the partial vapor pressures of the two liquids is what we call solutions with negative deviation. Non-ideal. So, this is non-ideal solution with positive deviation, non-ideal solution with negative deviation. When do we get positive deviation? Positive deviation graphically, if I represent, for an ideal solution, XB is equal to 1, XA is equal to 1. For ideal solution, already we have seen this kind of a graph, where this is say like PA naught, PB naught. But now in the case of non-ideal solution with positive deviation, the vapor pressures will be like this and the vapor pressure of the solution will be like this. This is the vapor pressure of the solution, means vapor pressure of the solution Ps is greater than, this is XA PA naught plus XB PB naught. Vapor pressure of solution is above this straight line. You are getting it is like a curve, it is not a straight line, where so Ps is greater than XA PA naught plus XB PB naught. This kind of graph if you get for mole fraction of B versus vapor pressures when you draw, if you are getting a curve above the straight line, normally what we get for ideal solution, this positive slope is what indicates that the solution is a non-ideal solution with positive deviation. So, we continue with non-ideal solutions with positive deviation. When do we get this positive deviation? Obviously, the positive deviation means vapor pressure of a solution is greater than sum of the partial vapor pressures of the two liquids. So, basically meaning is that it happens if the escaping tendency of molecules in solution is greater than that in pure solvents. Escaping tendency is more. when this can happen, when the escaping tendency will be more? Obviously, it is possible when the intermolecular force AB interaction is less than AA and BB interaction. AB interaction is less than the AA interaction and BB interaction. In this case, when AA interaction and BB interaction are more than that in AB interaction. So, what happens is that both A and B will try to escape out. When A and B are escaping out more, obviously the pressure will be more. So, in this case, what happens is delta H mixing will be greater than 0, delta V mixing is also greater than 0, and the vapor pressure of the solution is of course greater than 0. So, as in the graph that already we have shown, it is showing the positive deviation. Now, which kind of liquids will exhibit? So, in this case also what we can understand is the boiling point of mixture will be less than the boiling point of the two liquids. Boiling point of the mixture is less than the boiling point of the two liquids. So, here what happens is, when suppose if you take the case of ethyl alcohol and hexane case, what happens is in the pure ethyl alcohol there is a hydrogen bond, but in any hexane no hydrogen bond. But when you mix both to form AB, N-hexane will break the hydrogen bond in ethanol. So, as a result, what will happen when the hydrogen bond breaks? When the hydrogen bond breaks, what will happen? The escaping tendency of both the liquids will increase. As the escaping tendency increases, that more vapors will be formed, and as a result the boiling point will become less than the boiling point of the two liquids. Okay. Now, non-ideal solution with negative deviation. Non-ideal solution with negative deviation means PS is less than XA PA naught plus XB PB naught. PS is less than XA PA naught plus XB PB naught. In this case, the vapor pressure of the solution is less than the sum of the partial vapor pressures of the two liquids. So, the boiling point of the solution is greater than boiling point of the two liquids. For example, when you consider ethyl alcohol, water, the ethyl alcohol boiling point is about 351.2 and this is 373 Kelvin. Now, the boiling point of this mixture is somewhat less than the boiling point of the two. The reason being that the hydrogen bond between two ethyl alcohol and water molecule strengthen compared to that in 2 ethyl alcohol molecules. So, as a result, when you draw a graph, you will get this is P s is equal to x a P a naught plus x b P b naught, and this is P s is less than the what for ideal solution what you are getting. This is of course the pressure, right. So, the graph will be like this. So, here as I mentioned that ethyl alcohol water kind of systems where the hydrogen bond between 2 ethyl alcohol molecules will be less than the hydrogen bond between ethyl alcohol and water. So, it will strengthen, as a result the escaping tendency decreases, as a result the vapor pressure decreases and the boiling point will be more. So, this kind of mixtures are what we call, which shows negative deviation. So, this is about the non-ideal solutions with positive and negative deviations and their respective examples. The reason so very simple, when we get a non-ideal solution is that if the A-B interactions are not same as that A and B-B interactions, then in those cases we get non-ideal solutions with negative deviation. Okay? Now, this ideal and non-ideal solutions now follows azeotropic mixtures. What is azeotropic mixture? Azeotropic mixture is a mixture of two liquids, a mixture of two liquids in which both liquids boil at same temperature at a particular composition. When you mix the two liquids A and B, normally when you try to distillate, when you try to separate the two liquids by fractional distillation, liquid A boil at some temperature, liquid B boil at some temperature. So, upon heating, with increase in temperature, one component evaporates more than the other component. This is what is the principle we use in fractional distillation, or in other words, fractional distillation is a technique in which two liquids are separated from a mixture based on the difference in their boiling points. Now, if it is an ideal solution, of course, the two liquids will have different boiling points and the two liquids can be separated from one another from a mixture by fractional distillation. But azeotropic mixture is a mixture of two liquids in which both the liquids boil at same temperature at a particular composition. Now, here it reminds me that probably you people must have studied about manufacture of ethyl alcohol by fermentation process. Manufacture of ethyl alcohol by fermentation process, if you recollect, there we say that from molasses, what is molasses? 10% ethyl alcohol solution. ethyl alcohol is separated by fractional distillation till its concentration raise it to 95.6%. 10% ethyl alcohol solution is concentrated to 95.6% by fractional distillation. Means, as in the previous example that I have discussed, ethyl alcohol boiling point is about 351.3, water is 373. Ethyl alcohol boiling point is less. Ethyl alcohol boiling point 351.3, water boiling point, as all of us know, it is 373 Kelvin. Now, as the boiling point of ethyl alcohol is less than the boiling point of water, during fractional distillation, this ethyl alcohol evaporates fast. So, during fractional distillation, ethyl alcohol is more in vapor and water fraction increase in liquid fraction. This is how we separate it out. But my question here is that when 10% ethyl alcohol can be concentrated up to 95.6% ethyl alcohol by fractional distillation, why not we get 100% by same process? What I mean to say is 10% ethyl alcohol, when you can increase the concentration up to 95.6%, this is what we call rectified spirit. Rectified spirit. When you can get rectified spirit, why not absolute alcohol? Absolute alcohol means 100%. Rectified spirit you can get by fractional distillation, but you can't get absolute alcohol by fractional distillation. What is the reason? The reason is that when ethyl alcohol composition raises to 95.6%, then at 95.6% it forms a geotrope. It forms a geotrope, means the boiling point of both ethyl alcohol and water is same, that is 351.2 Kelvin. Both will boil. So, by fractional distillation you can't, if once it reaches to this particular stage, you can't separate out ethyl alcohol and water, because in this case what the main important point is that both ethyl alcohol and water composition is same in liquid and vapor phases. Ethyl alcohol and water composition is same in both liquid and vapor phases. So, the other way we can define azeotropic mixture as a mixture of two liquids whose composition is same in both liquid phase and vapor phase. Whatever the composition we have in liquid phase, same composition you will have also in vapor phase. So, as a result, when you keep on evaporating, when you keep on distillating the liquid mixture, same liquid mixture you will get in vapor state also. So, there will be no use of doing fractional distillation for that kind of mixtures. Means as you are getting the same, you are not able to increase the fraction of either of the liquids, so there is no use. So that kind of mixtures is what we call azeotropic mixtures. Now, so here what happens is at 95.6% when the composition reaches, both ethyl alcohol and water will boil at same temperature, that is 351.2 Kelvin. Further purification to 100% is not possible. So is the reason that fractional distillation is carried out only till we get rectified spirit. And if once you get rectified spirit, then to increase the concentration from 95.6 to 100%, that is absolute alcohol, we go for chemical methods of concentration. That is, we pass this mixture through calcium chloride, where the remaining 4.4% of water is absorbed, then you will get 100% ethyl alcohol. So finally the meaning is that you can't separate out water and ethyl alcohol from this, but for that to do, you have to go for a chemical method. Fractional distillation is not possible. That kind of mixtures is what we call azeotropic mixtures. Now, again in this azeotropic mixtures, we have two types. One is the minimum boiling azeotrope and another one is maximum boiling azeotrope. What is the minimum boiling azeotrope and what is the maximum boiling azeotrope? That we discuss now. This azeotropic mixtures again two types. Maximum boiling azeotrope and minimum boiling azeotrope. What is maximum boiling azeotrope and what is minimum boiling azeotrope? Maximum boiling azeotrope means the boiling point of liquid mixture is greater than boiling points of the two liquids. So obviously minimum boiling azeotrope is the one in which boiling point of liquid mixture is less than boiling points of two liquids. So this maximum boiling azeotrope is formed by solutions with negative deviation. Non-ideal solutions with negative deviation will form maximum boiling azeotrope, and solutions with positive deviation will follow this, will give this minimum boiling azeotropes. So whatever examples, whatever the characteristics, everything that we studied for negative deviation solution, non-ideal solution with negative deviation, they all will be maximum boiling, all things will applicable for this, and solutions with positive deviations where the boiling point is boiling point of the liquid mixture is less than the boiling point of the two liquids, that will form minimum boiling azeotrope. Solutions with positive deviation, solutions with negative deviation, right.